So this morning we heard three great talks about inferring demographic histories from allele frequency spectra. And while these spectra have been very effective at inferring demographies in the deep past, we are slightly more interested in more recent events. So we use a different kind of approach based on haplotype sharing. And other groups as well as ours have been using the workhorse of identity by descent between individuals in a cohort. And as Monty Slatkin explained eloquently yesterday, when you have siblings, cousins, and more remote relationships between individuals, occasionally you would see the ancestral alleles of the founders of these two lineages in the two descendants, the remote relatives, at the same, and when that happens at the same locus, these regions are identical by descent. Now, when these are long enough, we can observe them as identical by state. And so Kelly Harris and Rasmus Nielsen are in the audience, and they made the great contribution of really deciphering identity by state tracts into identity by descent regions. We're going to simplify things and assume regions as that regions that are identical by descent during this talk. First of all, because it's simpler. Second of all, when we're looking at regions that are long enough and with very recent common ancestor, it makes more sense to make that assumption. And last but not least, when looking at data, it's hard to generally say that a region that's identical by state is indeed identical by descent. When you simulate the data, you often can do that. Besides this introduction, we're going to review the model for what it means to be identical by descent in a population and how does that help us to infer demography. We'll extend the model from a single population to multiple populations, incorporating migration into the models, and actually look at some data from the Genomes of the Netherlands project. And finally, hopefully we'll have time to consider the large amounts of sequencing data and how they might be incorporated in identity by descent analysis that was invented in the dark ages of the SNP world. So let's start with quantifying identity by descent. And very clearly, if you know the relationship between individuals, things are easy. Siblings share half their genomes, and they share that half in very long tracts. And the farther apart are the individuals, the more remote is the relatedness between individuals, the fraction of their genome that they're expected to share decays exponentially by a factor of 4 every generation, because a site needs to survive each of the transmissions across the two lineages. And the expected length of the segment also decays, but decays only linearly, because the length of each tract is till the next recombination site, and the recombination events are a Poisson process for all intents and purposes. So can be the distance to the next recombination site is exponentially distributed with an expectation that is reciprocal to the number of generations till the common ancestor. So if we know the time to the common ancestor, everything is simple, but given all that we know about coalescent theory, we know a lot about the time to common ancestor. In a cartoon Wright-Fisher population of 20 individuals, the time to common ancestor is really the first coalescent event going back in time, and there are closed forms for that in this case, or in more complex demographical histories, for instance, exponential growth from starting population, ancestral population of size A equals 5 ancestors here to a current size 20 individuals at present during G equals 3 generations that this process may have taken. Importantly, whenever you have some model, some parametric model in mind for defining your population history, that allows you to use these parameters and start inferring a demography by inferring the parameters that will give rise to the data, the most likely parameters that will give rise to the data. The missing piece is really providing the likelihood to the observation, to the observed data of multiple segments of identity by descent, segments of different lengths. A key statistic here is the length of a segment of identity by descent around a randomly chosen locus between a pair of individuals. And if you consider a random chosen locus, then you need to walk to the 5' as well to the 3' end till the next recombination site and find the total length between those sites. So if you do know the time to the common ancestor, you know that and then everything is simple. What we don't know is when that common ancestor had really existed. So we need to sum over all options for that common ancestor and apply Bayes' rule in order to get just the total probability for a segment within any particular length interval between U and V. Further decomposing this expression, the left-hand part is just a coalescent theory. It's just the chance of a common ancestor being k generations ago, given theta, the parameters that we assume regarding population history. The right-hand side is also simple. We need to tally to the two exponentially distributed random variables that measure the distance from the current site till the next recombination site. So it's an Erlang 2 distribution, which whatever assumptions this would still, whatever assumptions we have about the demography, this would still hold. So it's instructive to look at specific cases, specific simplifications, specific assumptions to see what we can get out of this model. And of course, nothing is simpler than Wright-Fisher. And if you assume a constant population size, everything is closed form. As we've seen over the last couple of days, if you're really brave, you can open up Mathematical Live and solve this. If you're really smart, you can do that on the whiteboard. If you're neither, you can just recite the result and get a closed form for the chance of two individuals having a segment of length L between lengths U and V at a random point along the genome. So you can think of that statistic also as the fraction of the genome that would be in such segments within that range of intervals. So let's call that fraction f of UVF of that interval, and we can consider the expected fraction given that we know the ancestor had lived k generations back in time, or if we don't, the expected fraction of the genome in segments within that interval, just given the parameters that we assume regarding the population demography. So we can rewrite that, and a very useful case is when we're tallying up all the segments that we observe from a particular length cutoff and onwards. So when we take the right-hand side of the interval to infinity, so we can estimate or observe just the fraction of the genome in a data set that's in segments of a particular length and onwards. This is practically useful because if we limit ourselves to things that we can detect, and we often have that kind of a length cutoff, and for the constant population size case, this translates to a closed form estimator for the effective population size. For more complex cases, you can follow the same rationale. If you have some parameterization of population history, you can try solving the relevant integrals. In some cases, we can do that. The most general case is of an arbitrary population size at each generation. So we have a function n of k that tells us what is the population size k generations back in time. People may prefer continuous formulations or discrete formulation for the coalescent process. But I think because we're considering recombinations and later on mutations, the discrete formulation is actually helpful. The continuous time analysis relies on the fact that the events you're interested in are coalescent events. If those are the only events, then that makes sense as the clock. But when you have several different clocks that work at different rates, I think it becomes even more convoluted. So we try to keep the actual generation time as the clock here. So most generally, you can assume any population size at each point when you go back in time. And standard coalescent theory will tell us the distribution of the time to common ancestor given that distribution. And we can plug that in, though at least theoretically would still need to tally this summation till infinity. In practice, you can make the simplifying assumption that you don't need to go beyond a certain point, or formally that the population size is of a particular magnitude from some point in the past and further back, and which is how we formally deal with that. The outcome is that you have a finite number of terms here. So even if you cannot get an invertible expression for the population size or for data, you can definitely get a likelihood from any kind of formula, any kind of description of population sizes in the past. So we so far looked at the fraction of the genome that is within segments of identity by descent of a particular length range. That's a useful statistic, but not the only one. Specifically, this is choosing. So we're thus far choosing a random site along the genome and asking what's the chance of that being in a particular segment of a particular length. For many uses, we're looking at multiple segments, and we may be choosing different segments and asking what is the distribution of lengths of the segments that we actually see. So each segment is weighted once rather than being weighted according to its length. In order to compute that quantity, the distribution of the lengths of actual segments, we need to, of course, normalize the contribution of segments of particular length by the length of that segment, and then normalize this expression by the overall fraction of by the overall tally of this P of L given theta divided by L, tallied across all possible L's. And again, while this is a general formula, you can substitute for a particular assumption, in this case for the Wright-Fisher model, and get a particular closed form. Another useful term is just the number of such segments that you may observe in a data set. That's helpful because in many cases you have fuzzy edges. There's some work by Gil McVean's group that deals with that formally. But regardless, a perhaps more stable number is just the number of segments that you observe. All you need to do is to take the fraction of the genome that's in such segments, multiply by the length of the genome that we denote here by gamma, and divide that by the expected number of such segments. This requires making the assumption that these two quantities are that the number and total lengths of segments are independent. It's of course false, but at least for segments that are far enough apart along the genome, this is useful. And there's a paper from 2011 that makes that claim more quantitatively. So we can get an approximate number of such segments, and you can do some additional manipulation to get the full distribution of this number. Basically, we can assume this number to be Poisson, given that expectation, and get the full distribution of the total fraction of the genome that two individuals would share in segments of a particular range of lengths. So far for the perhaps baseline theoretical framework for a single population. Of course, when we when we look at data, more often than not, we're interested in modeling not just a single population, but multiple groups of individuals in context, and specifically when we're contacted by the Genome of Netherlands people, the data set consisted of multiple provinces, which we went to develop the theoretical framework for analysis of multiple populations, multiple demes. So the key is that instead of considering the chance for coalescent in a single population, we need to replace that with what you get from two distinct populations. And of course, when the populations are completely separate, it's not really interesting nor practical. It's much more relevant to assume some kind of migration patterns between the two populations, and of course we can assume whatever. What we're doing right now is using a matrix of migration rates between the populations. This can potentially depend on time and can therefore model post-migrations as well. The framework is exactly the same. You just get data that includes a multidimensional distribution, not just segments that are shared between individuals, but rather segments that are shared between individuals in each of the populations, or segments that are shared by individuals across the two populations. You can write the likelihood and apply ABC in order to infer the most likely parameters for the data. For the simplest scenario of two populations that have been separate practically forever and have some fixed migration rate between them, we see that we can infer the migration rate here up to 5% quite accurately, as well as the size of the populations. When you add some more complexity, have two populations of potentially different sizes with asymmetric migration and potentially asymmetric growth, starting from a common ancestor at some point G generations ago in the past, you can still follow the same procedure and infer the migration rates. So this is kind of an amalgamation of the accuracies for different rates that are all inferred at once, as well as the population sizes. And these are the current population sizes after what's usually population growth that we see in many data sets. So there's one more parameter that we may be interested in, which is the time from that split event, and we considered focusing on looking at different admixture, different split times that precede an admixture event that was just 25 generations before present, an asymmetric admixture event with 80% from one population and 20% of the gene flow from another, and we can play with different split times in order to try and see how that affects the data. In terms of the migration, migration rate, so the total total contribution of genetic content from this minority ancestral population, the 20% group, we see that we're able to infer that pretty robustly for different split times, even as far as back as 500, 600 generations ago. And this is in comparison to Carlos and Simon's PCA mix and tracts on the same simulated data. So I promised you to look at some data. The data set I'm about to talk about is from the Genome of the Netherlands project. The data includes 250 trios across the Netherlands. This is a map of Netherlands with the different provinces highlighted. There are 11 provinces from which we have roughly the same number of samples, and we're considering the parents from these trios, so about 500 individuals altogether. The data itself is sequencing data to half depth, so 14x. So at least for the transmitted alleles, you have decent depth to call them, even with a single look. The data had been trio phased and called based on a specific trio caller for that purpose, so leveraging the design to the extent possible. Still, we did not take in all the variants that had been called. We only thresholded variants at 1% or greater, because for our purposes, for calling the segments, this contained the majority of information, and the rarer variants contained much more noise. So we prefer to avoid them at this stage. Still, the genome is the callable genome is large. The cleanly callable genome is shorter. And every time we had regions where we had concerns regarding the depth or quality of the data, we trimmed them out. Now, when you do that and analyze lengths of segments, you need to be very careful, because the segments can only reach that point of trimming. So we throw away every remaining bit of data, bit of chromosome that was less than 50 centimorgans. So there were a few regions like that we had to throw away. It affected not just the regions, but every part of the genome that was potentially close to them. We try to be careful there. We called regions of identity by descent with germline. So germline is a tool that we developed in our group. When you're looking at unphased data, it has its issues. With phased data, we believe it performs both fast and relatively accurately. And here again, we had trio phase data, so we're able to use that. So while we're considering data from 11 provinces. For many of the downstream analysis, we will consider them as separated into south, center, and north provinces in Netherlands. I know there are a couple of Dutch people in the audience, so hopefully I'm getting that part right. When you try to consider each province separately and infer a constant population size for each based on relatively short segments of identity by descent, segments of 1 centimorgan to 2 centimorgans, you see the North Netherlands provinces with the slightly smaller population sizes, center in the middle, and the parts of south of the country have an inferred larger population size. And these are relatively short IBD segments compared to the others we've been looking at. So this is the more ancient history of the country. When you consider the more recent history, the segments that are much longer, we no longer see this pattern. So this trend, whatever it is has something to do with the more ancient history of a few thousands of years ago. When we consider the average number of segments between every pair of provinces across this table, this is a symmetric matrix, or within each province across the diagonal, we can conduct this analysis at different lengths, thresholds, or intervals. So these are the longest segments we considered, segments of 7 centimorgans and above. And just to give you some orientation, we have this time scale at the bottom. The shorter the segments, the farther back in time we would be going. So if you squint at this heat map, you can see that the diagonal is a bit stronger than everything else, and things that are off diagonal, the far off diagonal, are a bit greener, so less segments of identity by descent. When you go farther and further back in time, so shorter and shorter segments, you can see some trends and some surprising things. So here, let me draw your attention to these two data points between North Holland and Friesland that, in contrast to the overall pattern, these two provinces seem to share a lot with one another against the overall pattern. Moreover, they share more between one another than North Holland shares with itself. And this hasn't been the case for the more recent time frames. So when we looked at that and mentioned that to our collaborators, they showed us this ancient map of the Netherlands where there is actually a reasonable land bridge between these two provinces that is not there today because of the changes in sea level. So it's rewarding that you can see this relationship between populations in accordance to the time scale that's relevant to the actual events that led to that. When you go further and further back in time, you see that the overall picture also changes. Yes, the shorter the segments you are considering, the more of them you see, so the numbers are getting bigger and bigger. But also, it's now no longer the case that the diagonal is what's dominating the picture, but rather everybody's sharing with the north. Moreover, everybody's sharing with the north more than they share with themselves. So we're trying to come up with histories that would mimic that effect. It's we feel it's more robust to pull the provinces together so that we're actually analyzing a 3x3 table of north, south, and center with sufficient amounts, sufficient sample sizes and sufficient numbers of segments in between each pair of populations. The model that is explaining the data best is a serial founder model where there is overall migration from the south to the center to the north, each population expanding exponentially, and with some migration going on between South Netherlands and the center along the entire period. This is not the only model that would give rise to this particular history, but in terms of the parameter space that we have explored, this explains the data best with the fewest parameters. So, I understand. Yes. Okay.
Is there more population structure in the south than the north?
Is there more population structure in the south than the north? I'm trying to recall the.
It reminds me of, I guess Graham Coop's not here today, but in his IBD paper, they found there was like more IBD sharing with Britain and Ireland than within Britain, and they thought that was because like Britain has some Irish people, Irish-like people, and some others, and it was just more likely for like the Irish type people to share with them than to share with British people who came from elsewhere.
So saying, well, the population of the north, of the south that we're currently looking at.
Heterogeneous. If there's some north type people there and there's some others.
Could be. I don't remember the exact statistics, but that makes lots of sense. I think Iran may be speaking to this trend of migrations later on. So I have 2 minutes, 3 minutes? 2. All right. So let's spend 2 minutes talking about sequence data. The nice thing about mutations along identity by descent segments is that, well, they are always along either of the two lineages that lead from the common ancestor to the two segments, and the number of mutations that you observe would scale with the generation time to the common ancestor and the length of the segment. Now, if we try to estimate the chance of observing a mutation that at a particular site, that would depend on that would be twice the mutation rate per generation times the number of generations. But since the length is also a variable, we need to integrate that based on the distribution of the lengths of these segments that are exponential, and you can figure out that what's going on is that there are mutations and recombination events that may be coming, and we're waiting for the first recombination event among these events. So it all boils down to just a geometric distribution with the chance of mutation versus recombination. So mutation rate and recombination rate play a part in this, in defining this process. Most importantly, this does not depend on the generation time G. It just cancels out, no matter whether the common ancestor is ancient or more recent. If it's more recent, we'll be looking at shorter time for mutation, but longer regions for them to happen. It's slightly more complicated when we're considering the more practical case, where we're only looking at segments above a particular length cutoff. So we would have some mutations within that range till the length cutoff mutations that we would need to count anyway, and those would behave as a function of the generation time. But beyond that, we'll still have this competition between mutations and recombination events waiting to the first recombination from this point onwards. So what we get out of this is really a function of both the generation time as well as the geometric distribution, but the final outcome is something that's only weakly dependent on the population history and on the population size if we're modeling a constant size. More specifically, we can practically look at different population sizes and see that while the total number of segments is really a good indicator of the population size, the number of mutations that we see barely changes across this range of population sizes, in this case between 3,000 and almost 20,000 individuals. We can manipulate the expression further to get rid of this even small dependency on population structure. If we consider this segment from its start at 0 till the length cutoff u, and from the length cutoff onwards, and sort the different mutations through the two buckets, the one that depends on population size and the one that doesn't. And the bucket that doesn't is only a function of mutation rate, so we can, at least in simulation, infer mutation rates based on such data. I'm about to be thrown out of here, so let me just say that in practice, this had served us more to estimate noise rates than mutation rates, but that's already some kind of information. And just to sum up, the identity by descent is able to infer recent dynamics of one population or several. Within the Netherlands, we see the expansion within each province as well as the directional migration. When you incorporate sequence data, it's less informative regarding the historical patterns, but it is contributing information regarding mutation rate. And the vast majority of this work is by Pierre Palamara, who deserves all the credit. I also want to thank our collaborators from the Genome of the Netherlands, primarily Laurent Franchioli, who was really the leading persona for this effort, as well as the population genetics group, Sarah Pollitt, Clara Elbers, and Shamil Sunav's group, and Paul De Backer, who's been the MC here. Thank you.
We have time for a few questions. When you calculate the mutation rate from the IBD segments, how much of an issue is it that the detection of the IBD might be affected by the mutations in each segment? So if you have more mutations, you might do a worse job at inferring the IBD.
How much of an issue is that the detection of the IBD is affected by the mutation? So in practice, I think we're exploring beyond the limit of that question now, because right now we're seeing many more changes between many more differences between segments than is practical to expect as mutations. many of the changes we observe are sequencing errors. So I think in practice we're now in a worse situation than what you're maybe concerned by. So the segments we're looking at are long enough for the ascertainment, I think, to be of just of a secondary effect. Yep.
I'm also, we're currently extremely interested in estimating mutation rates. And a couple of comments. First of all, your 14x coverage is not, as I'm sure you know, not wonderful for what you want to do. In our hands, at any rate, we see substantially better calls at 30x compared with 20x. Diploid calls at 14x are not so easy. That's just a comment. But then, do you think that with deeper data, maybe more data, and maybe deeper sequencing, you could really get a handle, you could get the error rate low enough that the mutation rate will really be emerging?
Think is a strong word. Have done the simulation to evaluate? The answer is no. I think there's hope to get so it's to get the information content from a few thousands of false positive singletons per genome. If you go down to 1,000 or 2,000, then you're already in an interesting range here, because within each segment you expect very few.